only one time. Also define element for TQC, most of the people, especially senior people, just read the computation. Right? They don't have anything. So I think then the point is, yeah, I think there are many changes. I think we should discuss it content. Then it's like many things.
So is the second speaker around? Yeah, thanks. We'll have like 20 minutes, like 22, 23. I think I will show you by the clock over there. Okay, but I will show you 5 minutes. Yeah, and so I guess we start just 1 minute. So I'll answer you. Okay, let's start. So it's 1:30. It's time for the first afternoon session. Okay, and we will start with the work by Pulkit Sinha on proper and improper quantum pack learning. So please.
Yeah, hello everyone. So I'll be presenting a work on proper versus improper quantum pack learning. So let's start with a simple device characterization scenario. So say you're given a device with n ions in the ground state. Then you hit it with a photon and then observe that the photon has interacted with the device in such a way that exactly one of the ions got excited. However, you do not know which one. So it could be this one, this one, this one, or in fact, the resultant state can also be a superposition over these singly excited states. Now, suppose you're given further the information that there's actually only a subset of size k of these ions that's actually excitable. Further, you are also given the information that the photon interacts with the device in such a way that that the resultant state is a uniform superposition over all the possible singly excited states. The goal now is to learn via these samples, via samples of this resultant state, the set of excitable ions. So let's look at what the resultant state is going to look like. So the resultant state is going to look like a superposition over these ket E sub i's, where each E sub I is a one-hot vector, where a 1 corresponds to an excited state, while 0 corresponds to the ion being in the ground state. Now, information theoretically, learning from these samples is equivalent to something that is called the quantum coupon collector problem, where instead of the ket E sub i's, you are given access to superposition over the ket i's belonging to S. Now, originally, this problem was studied due to its relation to this other learning problem called quantum pack learning. So let's look at what that is. So let's look at a more general kind of superposition, but we are still restricted to amplitudes being positive real numbers. Here, the state ket psi is a superposition over the elements in a set X. Next, we consider labeled quantum samples for a function f, which is defined on a domain X and has output 0 and 1. Now, how do these labeled quantum samples look like? Basically, in ket psi, what you do is you replace each ket I with a ket I, ket fi. Notice that this labeled quantum sample is well defined for every binary function f. However, we are mainly interested in the case where this f belongs to a known function class, say C. With this, the problem of quantum pack learning is as follows. So given access to these quantum samples, what you're supposed to do is find an approximation f tilde to f such that the corresponding labeled quantum samples are close to each other. That is, their inner product is at least 1 minus epsilon. So classically, this problem has been well studied. That is, if you restrict to computational basis measurements, then it is known that the number of samples required for this problem, that is, its sample complexity, is order of d over epsilon, where d is a combinatorial parameter of the function class C, which is known as the BC dimension. In 2018, this result was extended to the quantum case. That is, it was shown that even with arbitrary quantum measurements, you cannot do better than order d over epsilon. Now, there is one thing peculiar about the algorithm that gives us the upper bound here. The known algorithm is improper. That is, the algorithm might output an f tilde that does not even belong to the same function class. This is bizarre because the algorithm uses the fact that f belongs to some function class, and in fact, it uses it to perform better, but however, still outputs an f tilde that it knows can never actually be the same as f. So let's look at this peculiarity in a bit more detail. So if you now enforce the algorithm to output an f tilde within the same function class, then that problem becomes the problem of proper quantum pack learning. Now, actually, classically, it has been shown that this problem is strictly harder than the usual quantum pack learning for certain function classes C. That is, for certain function classes C, with just computational basis measurements, the sample complexity has an order log 1 over epsilon extra factor required. Now, the lower bound for this is proven via something called the classical coupon collector problem, which is equivalent to using computational basis measurements in the quantum coupon collector problem I just described. So the classical coupon collector problem has a lower bound of k log k. Now, if we were able to find the same lower bound for the quantum coupon collector problem, then we would have also got the same proper learning lower bound in the quantum case as well. However, in 2020, it was shown that if the size of the complement is small, then actually there's a much faster algorithm for quantum coupon collector with arbitrary quantum measurements. So I'll not talk about our improvements. So for this algorithm, we showed an improved algorithm which further reduces the constant factor down to 1. Now, why is this interesting? We recently showed the same lower bound up to lower order terms. That is, we have now characterized the sample complexity of this problem not up to constant factors, but in fact up to lower order terms. Such characterizations are usually hard to find. Finally, this doesn't really solve the problem of proper versus improper pack learning, quantum pack learning either. So for that, we introduced a variant of quantum coupon collector problem, which we term as the quantum padded coupon collector problem. And for this problem, we show that the classical lower bound also holds. That is, the sample complexity is of order k log k. We also show that this lower bound does lead to the proper quantum pack learning lower bound that we wanted. So having described the results, let's first look at the algorithm. So for that, I'll first have to describe what the original algorithm did. So we are only interested in the regime where the size of the complement is small because that's where the speed up is. Next, consider the state psi to be the uniform superposition over all the possible elements that we are just working with the set n here. Now with this psi, we have that if you take the quantum sample for S and then you project it onto the orthogonal subspace of this ket psi, then approximately up to normalization, what you get is actually the quantum sample for the complement of S. Now, if this were exact, that is, you exactly got the quantum sample for S complement up to normalization, then you basically generated quantum samples of the complement, And then you can simply solve the quantum coupon collector problem on the complement instead, which is like very small. So it's faster to do. However, since this is not exact, if you try to use computational basis measurements on the quantum on this approximate state, you will definitely get at some point of time elements that belong to S instead. So the way the authors got around this was to just say, okay, when you sample these, just only consider the elements that are above certain frequency threshold, and that just works out. However, this incurs a penalty of factor 10. So to get around this, our algorithm has two main ideas. First, instead of sampling the complement with replacement, we sample it without replacement. This we do via by considering the complement under a smaller set instead of the whole set. Next, since this doesn't really fix the problem of the quantum samples being approximate, so we find a way to fix previously incorrectly sampled elements in further stages. So pictorially, you have the following scenario. So this entire rectangle is the set n of the first n natural numbers. Then the rectangle on the left side is the set S. So definitely the remaining one is as complement. And the blue region is kind of like the set you currently believe to belong to the complement, right? So now again, since you're making mistakes, there's going to be mistakes in this as well. So there might be a small region, which we are referring to R, that might have an intersection with S. Apart from that, there are some elements you just don't know belong to this blue region, to the complement. So those are in the red region as well. So this R we refer to as the rogue elements, which we have sampled so far, but actually lie in S, but we think they lie in the S complement. Well, C are elements we haven't seen at all so far. So having described this, let's look at the algorithm in a bit more detail. So the algorithm starts with the entire thing being in the red region and the blue region being like very small. So in each iteration, you ask for a quantum sample, and then you ask whether it belongs to the red region or the blue region. Okay. So if it belongs to the blue region, then that's basically a projective measurement. Then you have restricted yourselves to the intersection of S and the blue region. That is, now you have a quantum sample for the region R. So if you just sample it, you'll figure out, okay, this is an element I incorrectly sampled earlier. The other possibility is that you measure it to be in the red region. So if you measure it to be in the red region, then all you need to do is take the complement of S with respect to this U, which you do via projective measurement. And if the projective measurement goes through, then you approximately have a quantum sample for the set C, which almost always is going to give you an element in set C. So that is basically the algorithm. Now we move over to the variant of the coupon collector problem we described, which we termed as the quantum padded coupon collector. So the reason for defining this problem was that we wanted a problem that does give us the proper back-learning lower bound, but does not exhibit the same quantum speed up that shows up in the quantum coupon collector problem. So one of the key reasons for why the quantum speed up shows up in the quantum coupon collector problem is that all the possible quantum samples are actually close to one common single pure state. So to get around this behavior, we want our problem to have an adversarial scenario where some states can possibly be far apart. So the way we do that is by labeling each of the elements arbitrarily. So given on the screen here is a quantum sample for the original quantum coupon collector problem. We modify it by appending a ket li for corresponding to each ket I. This where L is a function from the set of n natural numbers to the set of first p natural numbers, which we refer to as the padding function, and each li we refer to as the padding. Now, once I've defined these quantum samples, the problem of quantum padded coupon collector is now just trying to learn S with instead of the original quantum samples, but not with the original quantum samples, but these quantum samples. Now, before moving on to an overview of the lower bound, I just want to point out one thing. So if L is injective, and if you do not touch the register containing the padding, then effectively you're tracing out that register. And since L is injective, that basically implies you're decohering the entire superposition. So it reduces to basically the classical sample. That is one of the other reasons why we consider these kind of samples. Now, moving on to the lower bound overview. So what we want to do is show that the lower bound for the classical coupon collector problem also holds here. So that is what we try to compare it to. So as usual, we consider for the lower bound, we consider an adversarial distribution over the input. Here, so we just choose the subset S and L uniformly randomly. Now, note that in the quantum padded coupon collector problem, you're not really supposed to find L. So what you can do is you can just take the ensemble average over L to get rho sub S, where rho sub S is just the ensemble average over T quantum samples corresponding to all different S's, all different L's for a fixed S. Now, with these rho sub S's, the problem of quantum padded coupon collector is simply just state distinguishing. Next, we found that if you apply the Fourier transform onto each of the padding registers, then the state that you get is block diagonalized. Moreover, we found that the blocks themselves were defined by something called the modular signature. That is, basis states belonging to the same block have the same modular signature. Further, we found that the support of this modular signature, like support in the sense, so modular signature is like a sequence of elements, and the support is the set of indices where it's non-zero. So we found that kind of counts as a proxy for a set of elements that have been collected in the classical coupon collector process. So what do I mean by that? So for any block, for any non-zero block belonging to rho sub S, the probability of sampling that block, for that block, the support is always a subset of S. Next, the probability of sampling that block, not just that block, but overall sampling blocks that have support some fixed subset S, that is approximately equal to the probability of sampling S in the classical coupon collector problem. Finally, we also found that the blocks corresponding, so non-zero blocks corresponding to the same modular signature but across different S's, they are basically indistinguishable. So that basically says measuring the modular signature is basically all you can do to distinguish these states. So that's basically end of the lower bound overview, and we're near the end of our talk. So to summarize, we have demonstrated improved and adaptive algorithm for quantum coupon collector. For comparison, the original algorithm was sequential and non-adaptive. Ours is still sequential, but we have an adaptive element now. Next, we introduced the quantum padded coupon collector problem, which has helped us show the proper quantum back learning lower bound. Something I did not mention here is that you actually need an approximation version of this quantum padded coupon collector to show the lower bound for arbitrary VC dimension. If you just use this version, you'll just get the lower bound for the VC dimension 1 case, so 2 case. Next, the specific function classes for which we show the lower bound are the padded function classes, which are something which we refer to as the padded function classes. Finally, so the function classes that we show the lower bound for is actually a much smaller subset than what is known classically. Now, recently, it was actually characterized for exactly which function classes show the separation of proper and improper learning. However, this separation is still, like this characterization of exactly which concept classes show the separation is open. So that is the end of the talk. Thank you, everyone.
Okay, thank you for your interesting talk. So we have some time for questions.
Hey, thanks for your talk. Is there any connection between the way you define this pattern coupon collector problem and hidden subgroup problem? Like you measure the second register, then you apply the Fourier transform, and then you do something based on that.
This none that I actually know of, but this was also pointed out by one of the reviewers, so I'm not exactly sure what's happening here.
I see. Thanks.
Any other questions? Okay, I have a couple of questions myself. So the first question is, so I don't really often see that you characterize complexity up to a constant, not up to a constant factor, but including the constant factor. So and didn't really understand, was it important for applications, or you did it just because you could did it?
I mean, kind of both. So like for like practical purposes, although this is like a toy model, but like for practical purposes, I guess like constant factors do matter for data, right? And for theoretical, yeah, this is just a way to showcase that our techniques are actually very tight.
Okay, thank you. And my second question would be, so do you think that your technique of adding extra padding can be used for some other problems beyond coupon warning? Would it be interesting?
I mean, I do think so. So basically, these if you add these padding in the classical case, that doesn't really impact hardness in any way because you can just get rid of it. However, in the quantum case, we do see that the padding effectively sort of decoheres the samples. So it might be useful in other cases where you want to like work with quantum representations of classical data and want to show hardness results.
Okay, thank you. And so maybe any other questions from the audience? Okay, if no more questions, then let's thank the speaker once more.
Thank you.
let's continue. So the second talk of the session is given by Wilfred Salmon, and the topic is advantage in quantum pack learning. So please.
Thank you. Yeah, thank you for the introduction and thank you to the organizers. So as Alex said, I'm going to be talking about advantages in quantum pack learning, and this is work done in collaboration with Sergei Strelchik and Tom Gurr at the University of Cambridge. And here's a link to the archive where most of this work is. So brief outline of the talk, we're going to start with a review of classical pack learning, which gives us the necessary background to then introduce quantum pack learning and very, very briefly touch on some of the advantages that already exist in the pack learning literature, but it's by no means an exhaustive list of those advantages. Then we're going to introduce our new access model for quantum pack learning, talk about our main result, which is a generic advantage for pack learning. And then I'll briefly give you the key idea in how we get our result. And conclude with some open problems that I think are worth looking into. Okay, so we'll start with classical pack learning, which is sort of the fundamental basis for most of modern machine learning. And it relies on two key assumptions. First of all, that a good model doesn't have to be exact. It's enough to be correct with very high probability. And also, your learning algorithm doesn't always have to output something that's correct. It's also enough for that to happen with high probability. If 99% of the time you output something that is correct 99% of the time, that's probably good enough in practice. Of course, this is a huge theory, so we don't have time to go through all of the different types. So we're just going to focus on the most studied type of pack learning object, which is called a classifier. Which is just an indicator function on some finite set. I mean, you can deal with infinite sets as well, but then you have to do measure theory, and I don't like measure theory, so we're going to do finite sets. And a classifier is just a 0-1 function on that set. Sometimes it's also thought as a subset, where you think of the pre-image of the number 1 as being some subset which is marked as yes. So for example, you might have X be the set of images, and F might output 1 on pictures of salmons and 0s on other pictures. So this would be a 1, and this would be a 0. Okay. Now, in most scenarios, not all inputs to your function are equal. You care about some a lot more than others. So for example, if that previous example I was talking about, you probably care about what your neural network or algorithm says on images like this. You probably don't care what it says on some random pixelated noise. And you're far more likely to get inputs to your algorithm that look like this than you are random pixelated nonsense. So this is modeled by some probability distribution on the underlying set, but it's very hard to write down what that probability distribution would be or even get a handle on what it would look like. So generally, we assume that this distribution is unknown, and we want our learning algorithm to work whatever the distribution is, but we just assume that there's some distribution out there. The moment you have a distribution on your set, that induces a distance between two classifiers, which is just the probability that they disagree if you draw a sample according to the underlying distribution. Finally, if we had no information about what our function is, the function that we're trying to learn, that would be an extremely difficult problem because there's doubly exponentially many possible classifiers. So to even describe a generic classifier takes exponential information. So for example, in the case of the pictures example I was talking about, we know that whether or not a picture contains a certain animal is a rotationally symmetric property. So we know that our function should be rotationally symmetric. And the most general way that you can tell someone some structure is you can promise that the function belongs to some subset of possible classifiers. And this subset is usually called a concept class, and elements of C are called concepts, which is basically just another word for classifier, and I'll probably use them interchangeably. So to recap, we've got some unknown concept in our concept class that we're trying to learn. A learning algorithm is going to receive some random data that depends on the unknown concept, and there's like a whole plethora of different access models that are considered in the classical learning community, but the one that started it all and the most famous one is random labeled examples, which is we're going to receive pairs of data points x, c of x, where x is drawn according to this unknown distribution, and we get told the label of that point x. The algorithm succeeds if it outputs a hypothesis H with error at most epsilon, so it gets something that's epsilon close. And because the algorithm is receiving random data, the output of the algorithm is a random variable in of itself, and we want that algorithm to succeed with probability at least 1 minus delta. I probably should have said PAC stands for probably approximately correct learning, and that P probably is that with probability at least 1 minus delta, and the AC approximately correct is that your output is correct most of the time. So to summarize, an algorithm is an epsilon delta learner if with probability 1 minus delta, it outputs something that is wrong with probability less than or equal to epsilon. And we want it to work for any underlying concept and any distribution. So as mentioned in the previous talk, the sample complexity, so the number of samples that the algorithm needs to draw was well, I should say that the sample complexity of a concept class is just the best possible learning algorithm. And that sample complexity was sort of pretty well described back in 1989 in this very seminal paper, which found this expression where I've defined epsilon and delta, but I haven't told you what D is. D is called the VC or Vapnik-Copernicus dimension of the concept class, and it's a combinatorial parameter, so you can just look at the concept class C and in theory read off what D is. It's a bit finicky, the definition, so I won't go into it, but it basically tells you how much structure there is in your concept class. So if your concept class is extremely structured, it has a low VC dimension and therefore a low sample complexity. And if it's got not much structure at all, then the dimension is very, very high and you need lots of samples to learn. Now, of course, oh, and yeah, the lower bounds from that paper, and then they also provided an upper bound, which was a log epsilon factor worse. But it actually took like 27 years to get rid of that log factor in 2016 by Haneke. This is, of course, all in sample complexity. Time complexity is probably a more realistic resource because you care how long your algorithm runs for, but it's extremely hard to prove lower bounds in time complexity, so we use sample complexity as a proxy to get some kind of handle on how these algorithms are going to scale. So on to quantum packed learning, and we'll have a slide about the good things in quantum packed learning. In 1995, two people, Bashuti and Jackson, introduced a generalization of packed learning to the quantum case. And instead of receiving these pairs, you receive this quantum state, which is chosen specifically so that if you measure the quantum state in the computational basis, you get back a classical random labeled example. And therefore, quantum algorithms can't be worse in sample or time complexity because you can always just measure all your copies of the states and then run your classical learning algorithm. But they could be better. And in fact, if you restrict D to being the uniform distribution, then we know that there are lots of cases where you can get quantum speedups, and those are provable in sample complexity. So I've written down some examples. So DNF formulae, K-hunters, you can recast Bernstein-Vazirani in this context as well. And you can even get exponential time complexity advantages, but these tend to be a little bit pathological and rely on things like factorization being easy for quantum computers, but hard for classical computers. And that's in time rather than sample complexity. Unfortunately, some bad news, which is if you go to the full model where you allow arbitrary distributions, in 2017, Aruna Chalam and DeWolf showed that you actually can't get generic sample complexity advantages. So they showed that quantum packed learners must draw at least this many samples, which matches the classical upper bound, and therefore you can only hope for advantages in prefactor or for time complexity advantages, but no generic information theoretic advantages. So this is where we introduce our different access model, and spoilers, we will find that there's advantage in our access model. We assume that you have access to a unitary that prepares the quantum sample rather than just the sample itself. So there's some fixed input state, which is probably cat0 tensor itself a bunch of times, but in general, it's just some state that you know how to prepare. And you have a unitary that when you act on that input state, gives you the quantum sample. More generally, we can cope with a unitary that adds some random phase and some random state garbage that we don't care about, which is quite important because often it's easy to prepare states with garbage, but quite hard to get rid of that garbage. And very importantly, we also assume you have access to the inverse of the unitary. And in our model, a query is equal to the oracle or its inverse, which is supposed to be roughly equivalent to the difficulty of preparing one of these quantum samples. So our main result is that in our work, with our access model, we get an upper bound that looks like this, which if you stare out hard enough and you've got a good memory, you might notice that 1 over epsilon is turned into 1 over square root epsilon. So we've got a square root advantage in sample complexity. And we get a lower bound that looks like d over square root epsilon, so up to this log bit that most people don't really care about. The bounds match, and the only possible advantage you can get is a square root in the epsilon parameter. So importantly, there's no possible advantage in VC dimension. And yeah, this is learning classical data encoded in quantum systems. So now that I've said that our model lets you get a square root advantage, that's a reason that it's a good model, but is it actually reasonable? If you, on the one hand, if you can produce the quantum state, you are probably doing it by some unitary process. It's very unlikely that these states popped out of nowhere. You probably created them with a black box process. And if that black box process was a circuit of 1 and 2 qubit gates, then it's probably easy to invert it because you just swap the order of the gates and replace each by their inverse. Of course, telling an experimentalist, oh, just run your experiment backwards, they may not be such a fan of, but theoretically, at least, it's easy to do the opposite. I would say it's unclear whether quantum machine learning of just classical data is actually going to be useful ever because of this problem that loading unstructured data into quantum computers probably takes exponential time. There's a stronger case to be made, I think, for when you're trying to learn classical data about inherently quantum systems. So for example, if you've got a spin system and you're trying to learn correlations between spins at very distant sites, that's classical data, the correlation between 2 points, but it comes from an inherently quantum system. And in that case, maybe you have an oracle that corresponds to something like Hamiltonian simulation of your state, and your data is inherently quantum, and you have the unitary in its inverse. So there are cases where I think it is conceivable that this access model could be reasonable. And I don't think there are many cases where it's reasonable to assume that you have access to these states, but not the unitary in their inverse. And finally, just as a kind of, we're not the only ones that are doing it. Other people are looking at this access model too in various different contexts. So for example, to just name a few, state tomography, channel tomography, and mean estimation. So that's estimating the mean of a classical random variable. All have recent works where you assume access to the unitary, the inverse of the unitary, and often also the controlled version of the unitary as well. We don't need the controlled version though. So I promised you the key idea for our proof. So there's going to be 2 slides on that. And one of the slides is going to be introducing this seemingly unrelated classical machine learning technique called equivalence queries. And then on the next slide, I'll explain how that ties into our work. So an equivalence query is an alternative access model for classical PAC learning. And instead of receiving this random labeled example, you get to submit what you think the underlying function is to the oracle. And the oracle either says, the thing that you submit doesn't actually have to be in the concept class. It's just some classifier. And if you get the right answer, the oracle just says yes, and you can stop your learning algorithm because you have the right answer. And otherwise, you're told, here's a place where you're wrong. So you get given an x, c of x, importantly, where it's different from your guess. And you can study this in the adversarial setting, where the oracle gets to pick this counterexample to be as little as helpful as possible. But we're going to talk about it in the random setting, where the counterexample is basically distributed according to the underlying distribution, but conditioned on being a counterexample. So if x is a counterexample, its probability is just a distribution renormalized by the probability that you're wrong. And if it's not a counterexample, then its probability is 0. It turns out that this model is significantly strong, exponentially faster at learning than random labeled examples. So in this paper from 2021, these 2 authors, Glush and Banker, show that you can get a speed up where the d and delta dependence is the same, but the 1 over epsilon has turned into a log to the power of 9, 1 over epsilon. And they conjecture that this log to the power of 9 can actually be made as small as log 1 over epsilon, but in their proof, they end up with a log to the power of 9. Why do we care about equivalence queries? Well, classically, you can simulate an equivalence query with random labeled examples by just repeatedly drawing, you have your idea of what the hypothesis is, and you repeatedly draw random labeled examples until you find one that is a counterexample. So you just do rejection sampling, and that will have the correct distribution. And you need to do that about 1 over epsilon times to either conclude, yes, I'm within epsilon of the underlying hypothesis, and I can just stop and say what I currently have is good, or I find a counterexample and I can proceed with my algorithm. But with a quantum computer using a Grover search-like technique or amplitude amplification, you can actually do that in 1 over square root epsilon time. So you get this square root advantage in the amount of time because you can just search for places that you're wrong. So if you multiply that time or number of samples to do an equivalence query by the equivalence query learning complexity, you end up with this, which is exactly the upper bound from our work. I hit a log to the power of 9 earlier. And importantly, if you manage to improve the sample complexity of the equivalence query learning algorithm, then our algorithm will improve as well immediately. And okay, there are some technical details that I'm kind of brushing under the rug here because obviously all of this is probabilistic, but that's morally the main idea of our algorithm. So I'll just conclude with some open problems. I think the most interesting open problem is, what if you don't have the inverse of the oracle? What if you just have the unitary that prepares the state? Does that reduce you to the power of just the copies of the state, or is it still the same as the full power of the universe and the inventory? The unitary and the inverse, or does it depend on the concept class, or does it depend on the particular implementation of the oracle, etc.? Is there a classical equivalent to the inverse of the oracle? Because we've given our quantum computing model more power, but it's unclear what we should give the classical learner as a equivalent new power. Can you generalize this to agnostic learning? The answer is probably yes, using mean estimation stuff, but that's a more realistic model of machine learning, so it would be nice to get similar speedups there. Can we get rid of some log 1 over epsilon factors? If the equivalence query people get rid of some log 1 over epsilon factors, that you can also immediately carry that through to our algorithm. But if you want to get rid of log 1 over epsilon factors altogether, it's going to require a new idea, because if you use just our approach and you want to get a 1 over square root epsilon, then you would need the equivalence query learning algorithm to have no dependence on epsilon at all. And that seems quite unrealistic. So removing all log 1 over epsilon factors probably requires a new idea. Can we translate some of these information theoretic sample complexity advantages into some more concrete models of machine learning and maybe some time complexity advantages instead? And yeah, thank you very much. And I'll be happy to take any questions.
Okay. Thank you for interesting talk. Any questions?
Hi, thanks for the talk. Could you talk about the lower bound proof at all?
Yeah, the lower bound comes, do you know what the VC dimension is?
Yeah.
Okay, so you take a set on which is shattered, so and you restrict the distribution to that set so that you have no information about, there's no structure on the learning problem basically. And then that just basically reduces to learning a bit string. Then you put you set the distribution to be basically all of the weight on one element and then a very small amount of weight on the other elements, but enough that you need to learn a bunch of them. So it's the classic lower bound distribution. And then you can show that the problem is equivalent to learning a bit string, and that there are existing lower bounds for recovering a bit string with a weak phase oracle. And we show that you can turn a weak phase oracle into a oracle that prepares that distribution, and therefore we reduce to recovering a bit string with a weak phase oracle, which is actually in the exact thing we reduce to is a result from the state tomography paper from von Apeldoorn et al., which is actually just a footnote where they don't give a proof, but they say you could prove this by doing 3 things. So if those 3 things do work, then that's what we reduce to. Yeah.
Awesome, thank you.
More questions, please?
Can you imagine any natural setting where the complexity would be sublinear in the VC dimension?
There are some cases of in boosting algorithms, which is where you have a bad machine learning algorithm and you run it many, many times and want to produce a good sample, where there's some existing work by Arunachalam and De Wolf, Isbeki, Mighty, that show some sublinear, so square root VC dimension improvements. But because we have this lower bound, we know that we can't get those sorts of square root improvements in this setting.
Thank you.
More questions? Okay, let's see. So I have a question. I guess it was your first open problem, whether you need, what happens if you reduce your ability to query the inverse circle? Yeah, so my question is, do you know of any problem where this gives any improvement? So not necessarily machine learning, but something else?
Yeah, so for example, in quantum metrology, if you are given, so the simplest example in quantum metrology is an unknown phase. So 1 over square root 2, 0 plus e to the I theta 1. And if you're just given copies of that state, there's no quantum advantage. But if you're given a unitary 1, 0, 0 e to the I theta, then you get a quadratic improvement. And you don't need the inverse of the unitary. In fact, the inverse is useless. You just need the unitary itself. And you already get the quadratic improvement. So there are some settings in quantum information, at least, where the unitary is sufficient. I don't know of any really quantum computing examples of where someone studied just the unitary but not the inverse and got an improvement. If anyone does have any examples, I would like to know. So please let me know. But yeah, I don't think it's trivial to understand where the complexity is going to end up.
Okay, thank you. That was interesting. So any one final question? Okay, if no more questions, let's. Oh, there is. Sorry.
Thanks for your talk. So is there any relation between having access to the Oracle and the inverse and classical membership queries?
I don't think so. Because so membership queries are when you can just query a label like an X and just get back what C of X is. So for example, if the distribution has no weight on an element, then it's impossible using the Oracle and the inverse of the Oracle to find out what the concept class is on that element. But with a membership query, you can obviously do that. So I think membership queries are kind of, I wouldn't say they're strictly stronger, but they're sort of incomparable, because there are some things that you can do with membership queries that, you know, if the weight of the distribution is very, very small, I think with just the states, it requires 1 over the distribution number of samples to get the value of that element. With this, you can probably turn that into a 1 over square root thing with a Grover, but I don't think you can do better than that. So membership queries give you a lot more than the Oracle and the inverse.
Thanks.
Yes, thank you. Very nice talk. So you had like a last point about quantum neural networks, maybe, or something?
Yeah.
Yes. So in classical neural networks, this VC dimension is actually not useful because it provides vacuous bounds, and people have thought about other kinds of, you know, complexity dimensions like a path norm and so on. Do you know if someone has looked at more useful ways to characterize the concept class of quantum neural networks?
I would guess that someone has probably done it, but I do not know exactly. I don't really know much of the theory of like practical quantum machine learning. So yeah, sorry, I don't know, but I would be shocked if someone hasn't looked at it. Yeah.
More questions? That's the question, I guess.
He's just scratching his head, yeah.
Okay, then let's thank the speaker again, and we wrap up.
Hello. Hello. is the third speaker here? Put your hand up if you're the third speaker. Have you put your slides on the thing? Is this you, TQC 24? Cool.
Hello. Welcome to the second part of the afternoon session. And we're gonna start with Adam Wills, who's gonna tell us about trade-off constructions for quantum locally testable codes.
Sound okay? Good. Not too loud, not too quiet. Thank you very much for coming. Is that too loud? No? Okay. Thank you very much for coming. Thank you to the organizers, and thank you very much to my collaborators, David Lin and Min-Shu Shane. So we're going to talk about quantum locally testable codes, and that's kind of niche. So I'll start by saying in quite a lot of detail what those are, and then why we care about them. I'll then go on to say what's been done in terms of building them, and then I'll say what our contribution is. So we provide these constructions that can turn one quantum locally testable code into another, and in some circumstances, you can get new parameters that were previously unknown to exist. At the end, I'll have just enough time to kind of whiz through the three constructions and say what they are and how we do them. So first of all, what are quantum locally testable codes? Well, they're kind of in the same ballpark as QLDPC codes, and I think that will be relatively familiar in this room. So the idea is that for fault tolerance reasons, you want to have every stabilizer containing only a small number of qubits and every qubit getting acted on by a small number of stabilizers. We're interested in this idea, but not for the reasons of fault tolerance, but for local testability. Informally, a quantum locally testable code are QLDPC codes with this extra property called local testability. And local testability, informally, means that you can detect errors by only acting locally, so by only acting on a few qubits. So a bit more formally, there is this randomized testing procedure, which I'll go on to describe. And it only acts on a few qubits. And if a large error has happened, then it will detect that large error with large probability. The degree to which a code is locally testable is measured by its soundness and locality. So these are two parameters I'll introduce, but the soundness is a parameter that if it's larger, it gives you a larger chance of succeeding in this test. And the locality, if it's smaller, it means you act more locally. So you're only acting on fewer qubits in this test. So to start with soundness. So soundness is to do with how many stabilizers you see being violated by an error. So for a general stabilizer code, if there's an undetectable error, then you'll see some number of stabilizers being violated. But in general, you don't have anything more than that promised to you. For a quantum locally testable code, the syndrome gives you a bit more information. So if a larger error happens, then there is a larger syndrome. So there are more stabilizers being violated. A bit more precisely, soundness is defined this way. So the code has soundness rho if for any Pauli error E, the fraction of the stabilizers that get violated, which is the left-hand side, is at least the soundness times the fraction of the qubits that are afflicted by the error. So that's the weight of the error divided by the number of qubits. So that's fraction of stabilizers that get violated is at least soundness times the fraction of the qubits that are afflicted by the error. So here's the same equation again. So how are we going to randomly test for errors? How are we going to look for errors? Well, the natural testing procedure to do is to pick a random stabilizer and measure it and just see if it's violated. And the probability you'll see it get violated is just this left-hand side. It's the fraction of the stabilizers that are violated. Then what we find indeed is if we have a large soundness row, the probability that we'll see a violated stabilizer, the probability that we pick up that an error has happened is large, assuming the error itself is quite large. In order to get all the way to genuine local testability, it's not just getting large soundness, but we need a small locality as well. So formally, locality is the maximum of the number of qubits involved in each stabilizer, or the maximum of the number of stabilizers acting on each qubit. So in particular, if you have a small locality, then every stabilizer only involves a small number of qubits. And so, as I claimed earlier, small locality means that your random testing procedure only acts on a small number of qubits. So why should we care about this? You can imagine a situation in which this is useful in QEC. I mean, it's not impossible to imagine that it's useful to be able to only interact with a few qubits and detect a large error happening with good probability. But this is speculative for a number of reasons, not least because these QLTC constructions are kind of crazy, so the constants are very, very bad generally. There's also the fact that we don't know how to do fault-tolerant computation on them. But yeah, they are much more interesting in the realms of complexity theory, especially Hamiltonian complexity theory. So a lot of people will know about NLTS. In 2015, Eldar and Harrow showed that if you have a QLTC, if you could prove one exists with some really nice parameters, then you'll automatically get the NLTS conjecture. There are also speculated connections between QLTC and the quantum PCP conjecture, which is this super important, super famous conjecture in complexity theory. The intuition here is that classical LTCs were indispensable in proving the classical PCP theorem, but it's kind of debated whether the same will be true on the quantum side. But as a baby step towards this, something that people are working on is trying to get like an NLTS plus result. The idea being that QLTCs were shown to imply NLTS in 2015. NLTS was then proved with codes that are weaker than QLTCs. So people are looking at maybe QLTCs can imply a stronger result than NLTS. But right now we're interested in just building QLTCs. And the early QLTCs look like this. So there's 4 figures of merit, and I explained 2 of them. The local testability ones are soundness and locality. And then there's 2 more which are very familiar from general error correction, dimension and distance. Dimension is the number of encoded logical qubits, and the distance is the minimum number of qubits that you need to afflict with an error in order to create a logical error. So these are the familiar ones. So the early QLTC constructions look like this. They only encoded a very small number of qubits, so only encoding like 1 or 2 logical qubits. And they had a square root distance. So that's kind of reminiscent of the surface code in a sense, but they're very much different to the surface code because the surface code has quite bad local testability properties, whereas these have good local testability properties. So the soundness is very good. It's polylog away from being optimal. And the locality is also still good, so it's logarithmically away from being optimal. There were subsequent works then in the following years that explored other areas of this 4-dimensional parameter space. You can imagine that for a while the situation was quite complicated because if you have 4 different parameters, you want to optimize all of them, but in the interim, you have a situation where some codes do some things very well and other codes do other things poorly. And there was a weird kind of frontier going on. Fortunately, now the situation is much more simple. Earlier this year, Dinurlin and Vidic introduced this paper that gave almost optimal QLTCs. And initially, they showed this dependent on a certain conjecture being true, but they updated their paper, not only removing this need for the conjecture, but also actually improving the parameters. And the parameters are as shown. So they get a linear dimension, otherwise known as a constant rate. The soundness and distance are almost optimal, both of them, so they're both polylog away from where they want to be. So soundness wants to be constant, distance wants to be linear, and they're both polylog away from that. And the locality went from a polylog to a constant in the second version. So this brings us quite close to the QLTC conjecture, which is this super interesting super hard problem in quantum coding theory about the existence of an optimal quantum locally testable code. So constant soundness, constant locality, linear distance, linear dimension. And this is a natural follow-on from the QLDPC conjecture, which was famously solved in 2021. And that just asks for linear distance, linear dimension, constant locality with no mind paid to the soundness. So our contribution is to give certain code transformation techniques. So we can turn one quantum locally testable code into another with different parameters. And these improve certain parameters at the expense of some others. And so we call them trade-off constructions. We have 3 of them. There is a weight reduction procedure for QLTCs. So this will push the locality down, so it improves the locality at the expense of some other things. There is a soundness amplification procedure, so this improves the soundness at the expense of some other things. And there's a distance amplification procedure, so again, improving the distance at the expense of some other things. And these are the parameter transformations that take place. So for weight reduction, indeed, the weight reduction can make the locality go all the way down to a constant where we want it, but it's at the expense of literally everything else, the soundness, the distance, and the dimension. For the soundness amplification, it indeed can improve soundness. And it's quite nice because it can actually maintain your distance and dimension, but it is at the expense of locality. And then the distance amplification can put the distance all the way up to linear, and it can do that while maintaining the dimension, but it makes both the soundness and locality worse. But if you apply these in the right ways, you can get new quantum locally testable codes that were previously not known. So in particular, we want to apply these to the DLD work. So this is their version 2 that I showed earlier. And suppose you hit this with distance amplification. So you can push the distance all the way up to linear, and that maintains the linear dimension, which is nice. But then that comes at the expense of the locality, so the locality rises. If you then further hit this with soundness amplification, then you'll hit the soundness and push it up to constant where it wants to be, maintaining the linear distance and dimension, and the locality stays as well. And this gives us like a very simple picture of what the status of QLTC is right now. So if you ask, how good are the quantum locally testable codes that we know to exist? We're not at a truly optimal one yet, but the status of this conjecture is summarized in this column and in this column. So you can either have perfect dimension locality, but then soundness and distance are slightly off optimal, or you can have perfect soundness, distance, dimension, but then the locality is slightly off optimal. So these are the 2 best. You might wonder, we had 3 constructions and I've only applied 2 here. The list of useful applications of the trade-off constructions has changed over time, and the reason is that the progress in QLTCs has been so rapid. When we initially posted the work last year, there were lots and lots of applications, and there were lots of things, new parameter regimes discovered with them. But that's changed over time. In particular, when the DLV work was posted in February 24, there was an application of weight reduction there. And also those were only known conditionally. So, some things were known conditionally and unconditionally for a while. So the situation was kind of complicated. But now the situation is much more simple, as I showed on the previous slide. So I can give a brief overview of how these all work. So the weight reduction procedure is based on Hastings on quantum weight reduction from 2021. And Hastings gave us weight reduction procedures for general quantum codes, but didn't analyze the change in soundness under these constructions, which means that you need to analyze the change in soundness to apply them to QLTCs. What makes quantum weight reduction difficult is you need to treat 4 things. You need to treat both qubit degrees and both check weights. So you need to deal with QX and QZ. So QX, for example, is the maximum number of X-type stabilizers acting on any given qubit. And then similarly, like WZ, let's say, is the maximum number of qubits involved in a Z-type stabilizer. And it's difficult. You need to get them all down to constant in order to make your locality constant. And that's hard to do because often a lot of the natural weight reduction procedures might reduce one of them, but it might come at the expense of another of them. So Hastings gives us 4 constructions, so 1 for each. So there's copying, gauging, thickening, and choosing heights and coning, and they reduce QX, WX, QZ, WZ. And the interesting thing is they have to be done in this order. And the reason is because some of them will hurt others, but some others require others to have already been done. And in general, it's a very difficult act to sort of balance. And yeah, as I say, we analyze the change in soundness under all of these. As for the soundness amplification procedure, so this is original to the paper. If I recall the definition of soundness, you can see that in order to increase the soundness, we're going to have to increase the number of stabilizers violated by any error without increasing the number of total stabilizers too much. We want this fraction on the left-hand side to increase, so we need the numerator to outrun the denominator. The way we do that is if we look at the stabilizers in our old code, we want to make a new code. We define stabilizers in the new code as combinations of stabilizers from the old code. And the combinations that we take are according to edges of an expander graph. And the nice thing about this is the stabilizer group doesn't change because we've just changed the basis of our group. We've changed the list of actual stabilizer generators, but we haven't changed the stabilizer group by doing this. And this is why distance and dimension stay the same because they're properties of the stabilizer group, whereas soundness and locality are properties of your list of basis elements. Lastly, distance amplification. So this comes from classical coding. So this isn't original to the work, but this goes back to the work of Alon Edmonds and Luby. So it's sometimes called the AEL, distance amplification procedure. And it was applied to quantum coding for the first time in 2022. And then again, we analyzed the soundness under this procedure so we can apply it to quantum locally testable codes. The idea is if you have your original code, then you break up your code into different blocks. And then each block you further encode into an asymptotically good QLDPC code. You then mix all of the qubits up, and you mix them up again according to the edges of an expander graph, which gives this nice pseudo-random mixing. And then you further encode each block. So again, each block gets encoded, everything gets mixed, and then the blocks get encoded again. And the pseudo-random permutation from the expander graph has the effect of lifting the linear distance of those inner asymptotically good codes to the distance of the outer code. The notion is that in order to create an error on the new code, you have to sort of fill up every block with errors because the pseudo-random permutation mixes all of the errors evenly amongst every block. That's everything I wanted to say. Thank you for your attention. Please do send me an email.
Thanks for the great talk. Do you have questions?
Yeah. Okay. So there was a paper, I think last year or earlier this year, from the Xanadu guys on another weight reduction scheme which works by you kind of weight reduce the classical codes before you do a product rather than weight reducing the quantum code. And this gives much better constant factors relative to the Hastings scheme. I guess maybe for your kind of asymptotic stuff, you don't care about this so much. But do you have any idea how that would compare to the things you do? Does this preserve soundness and things as well? Or you don't know?
Yeah, no, this is really interesting. So yeah, again, so this paper was weight reducing classical codes, and then before you take the product, of course, then that only applies to product codes. And I think they only did it for the normal homological product, right? So it wasn't for
They do lifted product.
They do lifted product and balanced product?
Yeah, and just normal hypergraph.
Did normal hypergraph or?
Yeah, they do normal hypergraph as well.
Okay. Yeah, no, so that would then apply to classical codes going into the homological product and stuff. So that is probably, I would imagine, the optimal one that you want to do for hypergraph product code. The quantum locally testable codes that we know are very much not product codes really at all. I mean, the DLV work is a complex. It doesn't come from a product. And the other thing is that it's not clear, like if you have a classical locally testable code, you take a product, it's not clear that you can get a quantum locally testable code from that. So their scheme wouldn't apply to quantum locally testable codes. However, like as you say, the constant factors are much better. And so if you're just interested in weight reducing a hypergraph product code, it's almost certainly just optimal to do that. Yeah.
I've also got like a somewhat vague question. So this like soundness condition reminded me a little bit to something like people consider in the context of like self-correcting quantum memories, which is that like if you violate more and more, if you make more and more errors, your like energy barrier increases. Is this a connection you have like thought about?
Yeah, very much so. Yeah, there's a strong connection. Soundness is like, there's like a lot of closely related properties for a quantum code to have. There's energy barrier, which you mentioned, and self-correction, and then there's kind of similar in this soundness. And there's links between all of them. There's like, some of them are formally linked. So I think, for example, if you have like good soundness, good distance, then you immediately have good energy barrier, I think. But some of them are more like moral, like it just seems these are kind of similar, like soundness just kind of seems like single shot decoding. They just kind of, they seem linked. As for, and what I would say is that soundness also does kind of seem like the strongest of them morally. But like whether you can actually make a self-correcting memory out of a QLTC, well, it's not obvious at all, but yes, there definitely is a connection.
Well, thanks.
I can like comment on that a bit more. So there's a property called confinement, which is sufficient for single shot decodability. And the kind of broadly like confinement and soundness are kind of, they look quite similar. But confinement, well, soundness is telling you that big errors have to have big syndromes, whereas confinement is telling you that big syndromes have to be caused by big errors. And the cases that are covered by soundness but not by confinement are kind of the cases that you miss in the like asymptotically good codes. That means they're not locally testable. And I think exactly the connection between single shot decodability and soundness is not known, but definitely confinement implies single shot decodability.
Yeah, I second that. Yeah.
Right. Any more questions?
Hi, thank you for the nice talk. I have a small question on the AEL amplification technique you used. So basically you can use that to sort of get a like a qubit QRDPC code, but with a very high relative distance. So can you comment on like how high the distance can you get to?
Do you mean in terms of like constant factors?
Yeah.
Yeah, so actually you might be interested in this paper. So this was the first time they applied AEL for quantum codes, and they were looking at that. They were looking at the constant factors. If I'm remembering correctly, whatever relative distance you put in your inner code, I think you literally inherit that relative distance for the broader code. So whatever you can put in there, you can get to the bigger one. As for exact numbers, definitely look at this paper. I hope I'm not about to misrepresent their paper, but if I remember correctly, what they were roughly doing was taking an asymptotically good QLDPC code, so it already has linear distance, but then amplifying the actual constant of the distance using an inner code that was, I think, like quantum Reed-Solomon code or something like that, to amplify the actual constant of the distance. And so they were seeing like, can we actually push the constant all the way up to like the quantum singleton bound or something like that? But yeah, as for the actual numbers, I would say see this paper.
Okay, thank you. I did see this paper, and well, they have like 1/2 distance close to that, but their alphabet is really large. So here you did like your output is a qubit code, so you also reduce the alphabet. So yeah, that's I'm asking, like, how well can you do for qubit codes?
Yes, sorry, yes. As you say, yeah, the alphabet for this is large. And the reason for that is we have a slightly different method in this third step. We encode again into a good code. And what you can also do, the alternative, is in the third step, you take each block and you just call it a larger symbol, which is what they do. And as you say, that leads to a big alphabet. So what could we get to? Well, we can't get, using this, you inherit the relative distance of whatever you have on the inside. And because we have to do this encoding again in order to keep the alphabet binary. So yeah, the relative distance that we would get would be whatever relative distance you're putting on the inside. So the answer to your question is, yeah, just look back at any of the asymptotically good QLDPC codes, Panteleev and Kalachev, DHLV, whatever you want, and that would be it.
Okay, thank you.
Are there any more questions? Doesn't seem to be the case. So let's thank Adams again.
Testing.
Right, so the next talk is going to be by Chris Patterson, and it's going to be about hierarchical memories simulating quantum LDPC codes with local gates.
Great, thanks. So thank you everybody for coming. So I'm going to tell you about how we can get some of the advantages of quantum LDPC codes, but in architectures where our gates are only geometrically local. So this is joint work with Anirudh Krishna and John Preskill, and you can see our work on the archive. So first, let me begin by just defining a quantum low density parity check code. It's simply one where each check is of constant size and each qubit participates in a constant number of checks. And in particular, we now know as of 2021 with the work by Pentelev and Kalichev that good quantum LDPC codes exist. So that is one that encodes a linear number of qubits with a linear distance. So we care about the QLDPC property for a few reasons. The first one is that we automatically have fault-tolerant syndrome extraction. The way you can think about it is that if we have an error in our syndrome extraction circuit, this can only propagate to a constant size region. And then furthermore, each qubit itself is only participating in a constant number of gates. So there's not too many errors that are accumulating. And then furthermore, the QLDPC property gives us kind of automatically a threshold under depolarizing noise. So this is this work by Kovalev and Priadko, and then later used by Gottesman in a work I'll talk about soon. So the other thing that we usually get for free is that the QLDPC property, whenever we construct our codes with expander graphs, this lends itself to efficient decoders. So in particular, we can oftentimes use a greedy approach to decoding, just flipping bits to reduce the syndrome until it gets reduced down to 0. So some of you may be familiar with the so-called small set flip decoders. We'll see one that looks a lot like this later today, I believe. So finally, Gottesman showed in 2014 that if we have a code with constant rate and polynomially growing distance, that this allows us to do fault-tolerant computation with constant space overhead. So we would really like to see, can we realize this in the setting where we're limited by only geometrically local gates instead of the long-range gates that Gottesman assumed. So locality itself is a bit of a curse. So what we do know is that there is various bounds on our code parameters. So if we have the parameters that Gottesman needed, the tannograph of our code must be an expander. So this is potentially quite challenging if we have a geometrically local architecture. So in particular, I personally believe that asymptotically, any truly physical system will eventually be geometrically local in some sense. Because if I have two agents with two quantum degrees of freedom and they're separated by some distance, the degree to which that you can couple these two things will fall off as the distance. So this is quite bad if we want to implement something with a high degree of connectivity. It's also kind of good because this allows us to build isolated systems. So if we have a system where as we scale it up, all our degrees of freedom are talking to each other, then our noise will be increasing as well. So it does help us out in some aspects. So non-asymptotically, we can take various approaches. For example, you can move qubits, like if you have ions or neutral atoms, you can use some sort of photonic things, or you can, just build long wires. But ultimately, at the end of the day, our useful model is going to approximate what we can do in practice. And in particular, I'm interested in proving asymptotic theorems, where it will be geometrically local as you sort of zoom out. So our main result is as follows. Given a good QLDPC code family and noise that's this particular model called locally decaying noise, you can just think of it as your gate errors happen independently, or maybe they're allowed to have some small correlations, but not too bad. Then there exists a family of quantum CSS codes with polylogarithmically vanishing rate and relative distance. So almost as good as you can get, but not quite. And we have a syndrome extraction circuit that you can implement in 2 dimensions with nearest neighbor gates. And we have a threshold. So in particular, you might see this, that this is actually a bilayer lattice, but that's fine. I can emulate this two-layer connectivity with just a single layer at the cost of some slightly worse constants. So here our below threshold scaling is almost exponential in the block length, but not quite. Okay, great. So now if I compare to what's been known before, on one hand, we have surface codes. They have 2D implementation with nearest neighbors gates, and the checks are geometrically local. So they're subject to the Bravi-Poland or Hall bound, and consequently, we have sort of this vanishing rate and not so good error suppression. On the other hand, we have our good QLDPC code, and naively, you need long-range gates because the checks are not geometrically local, they're only local, but we have exponential error suppression, and we also have constant rate. So our result kind of fits right in the middle here. We get nearly the best of both worlds. We have a 2D implementation. Our checks are not geometrically local, so that's how we sort of have parameters that are seemingly incompatible with the BPT bound, is that we don't satisfy the preconditions for this to apply. And we have this really nice rate and error suppression. So in general, you can ask, all right, well, I have my good QLDPC code. Let me just try to implement it in 2D without any concern for thresholds. What goes wrong? So we know from this work by Delphas, Offerland, and Tremblay that there's a space-time trade-off for any good QLDPC code in the syndrome extraction circuit, that if we don't have a large amount of installers, then we're stuck with the square root n depth of our syndrome extraction circuit, and there's no way to get around this. And the intuition is quite nice. Essentially, whenever we need to embed into 2 dimensions, our Tanner graph, and in 2 dimensions, the 2-dimensional, like a 2D graph, is not expanding. And in particular, there exist regions for which the number of vertices in this region and the boundary of the region are differ by quite a lot, by a polynomial amount. So in particular, here I found some region B where its boundary grows as the square root, whereas the size is linear. However, we know that if we have a good quantum code, the amount of connections outside the region, our Tanner graph must be an expander. And so we have a linear number of connections that we need to implement. So this looks something like this, where we have a large number of edges, a linear number of edges, and we have this square root number of gate or sort of connections that we can implement these things with. So that's how we get square root. So what we'll do is, as a first step, we'll just try to implement this thing naively. So we will start with our syndrome extraction circuit that requires long-range gates, and we'll just implement the long-range gates by doing a ton of swapping. So we'll, in particular, for any single 2-qubit gate, we'll take the targets of that gate, bring them together, and then use our local operations in order to implement the gate. And so kind of what this looks like is first I'll construct this circuit later, but let's assume that we have, and so in particular, what's going to go wrong is that the depth is going to be quite large. So we have our square root n by square root n lattice, and we populate it with a bunch of qubits. And what's going to happen whenever we do the swapping is if we saturate the DBT bound, we're going to have this polynomial depth circuit. And in order to have a threshold, we need that the noise per unit time is constant. And so what we're going to do is we're going to replace every qubit by a surface code of size just large enough such that we get the constant error per syndrome extraction cycle of the LDPC code. So first, I need to construct for you this syndrome extraction circuit. So let me do that. So with the long-range gates, the way we do it is for every operator, we're going to, for every check to measure, we're going to introduce an ancilla, do some entangling gates on its support, and then measure the thing. So we just have to schedule the entangling gates. We can do this by solving a graph problem known as an edge coloring. And this is efficiently solvable for a bipartite graph. And what we do is we simply, in each step, for each coloring, we schedule all the gates of the same color in our time step. So 1, 2, 3, 4, and then we measure ancillas. So we have a syndrome extraction circuit that uses the long range gates. Now we need to make it local. So in particular, I'm going to implement sort of arbitrary permutations. So this is this permutation routing problem. So for a 1D graph, a path graph, you can think of it as we have pebbles with addresses that they need to go to, and the vertices are also labeled, and then we permute them. So it looks something like this, and we just swap along the edges at every time step. So for 1D, this is actually quite straightforward to do. We just do a what's known as an even-odd sorting network. So it's pretty standard techniques. And then we can use this result of Anekstein and Baumslag from the 90s that tells us how to route. If we have a graph that's the product of two other graphs that we know how to route on, we can use those as subroutines to route on the full graph. So here, I've drawn in two pebbles that need to go to some destinations. You'll notice that they need to go into the same row. So we're going to take a step in G, a step in H, and a step in G again. And what this does, this first pre-routing step, is that whenever we take the step in H, they need to go to the same row. And so this pre-routing step kind of avoids this collision here, and this is all efficiently computable. So, okay, so now if you apply this to the 2D setting, for the 1D line, we can just use our even-odd sorting network. In 2D, we can just route along the rows, the columns, and the rows, because it's the product of 1D path graphs. And we get our depth is the side length of our lattice. Okay, so that completes the syndrome extraction circuits without any sort of surface code yet. So just for the surface code, you have an L by L surface code. This has a 2D implementation. And the only thing you really need to know is that we can do Clifford operations with polynomial resources. So we can compare, we can measure, we can do our C0, these sorts of things. And then below the threshold, we have this exponential suppression in this parameter. So all we're going to do is pick the side length of this thing to be polylog. You recall this expression here, the error rate per constant time, or sorry, the error rate per syndrome extraction cycle of the inner code times the depth. And this can be made, if we pick the surface code size appropriately, this can be made an arbitrarily small constant. So you recover the threshold. So now we can look at optimizing the constants. So everything in our paper is efficiently constructible. And we particularly spent a lot of time giving explicit layouts that had good space overhead, because we were hoping that maybe this is useful in practice. So here's an example of one of our gadgets for swap. If you're interested, you can take a look at the paper. And we also have sort of a tunable trade-off between, if you give us a gate of some length R can be constant, it can be growing, doesn't matter. We can use that to kind of make the world smaller by a size R. So everything gets sped up by factor. And then there's this question of whether or not it's practical. You may have seen Nadine's talk yesterday. This is this soft output decoder for the surface code. And the point was to gain to use this to more efficiently decode the outer code. So in practice, we're going to use some sort of belief propagation or something like this. We use the soft output decoder to give a better prior to BP. And in practice, it seems to be working pretty well, but we don't quite have, I would say, a firm idea of whether or not this is truly the thing we should do. Perhaps with, so certainly in the case of local noise, it gets local noise surface code is very good at recovering from, but you might imagine some sort of like rare events or something like this. So in the latest experimental paper from Google, they saw these tail events that wiped out patches of qubits, and then some sort of concatenation really starts to make sense. But so I'll say that we really need to look at this a little bit closer and do some pretty hardcore simulation before we're sure. So just to summarize, we built these syndrome extraction circuits that required the long-range gates. We embedded them, which incurred a blow-up. So we constructed circuits that were optimal according to the TBT bound. And then we cured this noise that we introduced by having such deep circuits by concatenating with a small size surface code. And the analysis itself, so I showed you something pretty sketchy. The actual analysis itself is sort of a coarse-grained approach using some techniques of Gauss-Smith from 2014. And here's our parameters. And the one thing I want to say about this is that, to my knowledge, this is the first time that surface code has been beaten in the geometrically local setting. So that's pretty nice. And there's two observations that I think are quite cool, is that, so one of the things, so one takeaway is that your checks don't have to be geometrically local in order to have a threshold in 2 dimensions. So this is related to a concept known as quantum locally recoverable codes, these QLRCs, where you have sort of something that looks, it's a relaxation of LDPC, where you have each, you have some constant weight checks, but then you also have some larger checks. So you're able to correct a lot of the errors using the local checks, and then kind of the high weight checks do the rest of the job. In our case, our code is not LDPC. It has some constant weight checks, and then it has some log size checks whenever we concatenate. And these log size checks we're not doing as frequently. These constant weight checks we're measuring all the time. So this is also related to this partial syndrome measurement of Berthus and encompassment. The other thing is that just constructing a memory with a high encoding rate and good error suppression is kind of the bottleneck for constructing low space overhead fault-tolerant computation in 2 dimensions. So we also can use our memories as ingredients for sort of new threshold proof with better space trade-offs. With that, I'd like to take any questions. Thanks.
Hi, thanks for the talk. If the syndrome extraction depth is square root n, would that potentially be a bad thing if one is trying to do logical gates? Like it would slow the clock speed?
Yeah, that's a great question. So in particular, if you have a single shot decoder for your outer code, which we now have, you'll see in perhaps a little bit, then actually the asymptotic scaling with the error rate per sort of, of the logical cycle with the error rate is actually the same as surface code, you'll find. Because actually I think it's slightly better. Unfortunately, I can't do this live, but it's better, it's as good or better than surface code asymptotically. In terms of constants, it is worse.
Okay, and maybe another related question. Could you imagine doing these long range checks after the concatenation with the surface code using like a lattice surgery, like a kind of constant depth thing, but is there an issue with that?
Yeah, so one is that you can absolutely do this with lattice surgery. It gives you worse constants, worse space overhead. You would not want to do it in constant depth because it's much harder to most efficiently use all of the you would like that your 2D lattice across every cut, you have the maximum amount of entanglement going across it at every time step. And with lattice surgery, it's very hard to do this if you're measuring one stabilizer generator per unit time.
I see. Okay, thank you.
Any more questions?
Hi, thanks for the nice talk. I have a small question on the rate parameter. It's like 1 over log n squared. And like in your previous slides, you mentioned that the surface code should be, the distance should be as large as polylog n. So is this like you pick a specific distance of the surface code, and is the rate, is the current rate on your slide the best we can hope for based on surface codes?
So there are ways to get better rate than what we have in our analysis. In terms of a comparison to surface code, if you picked so surface code is a 2-parameter family. If you picked a single parameter family that matched our rate, you would have very, very poor error suppression for surface code. I'm not sure if that answers your question.
Yeah. Okay, thank you.
I have one small question. So you like show that there is a threshold, but do you know like what the value of the threshold is? And is it like comparable to that of the surface code?
It's equal to that of the surface code because you can always increase the inner surface code. Yeah, it's kind of a boring number.
Right, and the fact that you have to route stuff along, like while still decoding the surface code, that doesn't decrease the threshold?
Not at all.
Any more questions? Doesn't seem to be the case. Then let's thank Chris again for the talk. Hello. So the next talk is going to be by Noah Bertheson, and the title of the talk is Toward a 2D Local Implementation of Quantum LDPC Codes.
Thanks. Can you hear me? Yep. Yep, so I'm excited to tell you all about our work that we've been doing at Maryland with these co-authors toward a 2D local implementation of 2D quantum LDPC codes. We just heard from Chris about a very similar paper, and we are trying to accomplish the same thing, but we have some different methods, and it's less asymptotic. So just as another introduction to LDPC codes, quantum LDPC codes, we're going to need quantum error correction for large-scale quantum computations. Even if we improve our gate fidelities and our device performance, we need to drive down the error rate to do large algorithms. So in the past, the choice has usually been the surface code or some topological code like the color code. And this is really nice for certain architectures like superconducting qubits because we can implement their syndrome extraction circuits in 2D. And for these computers, you can only do gates between qubits that are neighbors on the chip. The issue for this is these topological codes have pretty poor asymptotic parameters, and they obey this rate distance trade-off. So we have the surface code is really the best choice for this, and it saturates this bound. So then as alternative, these quantum LDPC codes have been introduced, and they have way better rate. They have constant rate, and they can achieve distances that are better than the square root of n. And in the past few years, they've even found codes where we have constant rate and linear distance. So these are much better performing than the surface code. The drawback for these codes is that if we want to implement them on 2D local architectures, if we want to embed them into these architectures, then to measure the stabilizer generators, we have to interact qubits that are potentially very far apart on the grid. And for certain architectures, this is not a problem, like neutral atoms or ion traps, because we can just move them around. But again, for superconducting qubits, this is a problem because we have to somehow entangle qubits that are far away just using the 2D local gates. So in our scheme, we also use a bilayer architecture, and this has been proposed for a number of QEC projects, including these hyperbolic codes, these concatenated codes that we just saw, and then the bivariate bicycle codes, which also aim to be implemented on superconducting hardware. And just as to define what we're working with, we're going to have two layers where the bottom layer contains our code of choice, or our data qubits and our check qubits, and then we're going to have a top layer that's just used for extra routing and syndrome extraction. We assume 2D local gates, so we can only perform entangling gates, CNOT gates between qubits that are adjacent on the grid. And the two layers can interact between qubits that are like this, under each other. And these are the only really gates that we're going to allow. And this sort of thing is physically realizable on superconducting architectures. We're going to focus on that for the talk. And it's difficult, it's difficult practically to implement, but it's feasible. So how exactly are we going to do QEC on the bilayer architecture? We need to measure syndromes, we need to perform logical gates, et cetera, everything with the QEC code. But we don't really want to use swap gates to move qubits around. If we don't do some special extra steps like we saw before, we're going to incur too much overhead because the swap gates incurs a lot of noise and the circuits are pretty deep. So instead, we can use constant depth gate teleportation, and this was actually used before in this Delphos Beverley-Tremblay paper. However, they found that using constant depth gate teleportation didn't yield a threshold, and doing this just incurred way too much noise in our error correction scheme. So we introduced a few new improvements to find better results, and this includes a purification of the bell pairs used in this constant depth gate teleportation. We do apply this partial syndrome QEC. We use different LDPC codes than they use in the paper, and then we provide this generalized routing algorithm for our syndrome extraction. So just as a very explicit example, we have two circuits that measure the X and Z stabilizers of some code, and we see that in this basic bare ancilla scheme, we need to interact our ancilla qubit with each of the data qubits. So if we can move the ancilla around, then it's fine because we can just perform these gates natively. But if we want to do it on this 2D local architecture, say we want to perform a CNOT between the blue and the red qubits, then we first have to move the blue qubit into position, perform the CNOT gate, and then potentially move it back. And then each of these swap operations can be decomposed into 3 CNOT gates. So we can imagine that the error that you're going to accrue throughout this process is pretty high. So instead, what we can do to potentially save some time and some error is we first construct this bell pair between qubits on the grid that are close to this blue and the red qubit, and then we can just perform gate teleportation to teleport a CNOT between them. And just as a hint, we can make this bell pair in the second layer of our bilayer architecture. And if we can do a bunch of them in parallel, then perhaps we can make it worth our while. So yeah, we need to figure out a way of constructing all these bell pairs in parallel, essentially. And this process, in general, can be referred to as teleportation routing. And as a simple example, suppose we want to measure this generator, denoted here by the blue qubits. We want to measure them with an ancilla indicated by the red qubit. So we can do this in 3 steps, essentially, by generating these bell pairs. Well, first by generating a bell pair, performing the CNOT, generating the next one, doing this one, and then the last one. And so it's pretty simple to just do one. But if we have a bunch of generators, it's less clear on how to do this efficiently. And we can consider the depth required to measure some generators in this way. And a very simple way of doing this is just to count the number of, or the length of the bell pairs essentially that you need to measure them. So if we have some function f of gamma that is the distribution of the sizes of the generator when we embed them in the grid, we can see that measuring one generator requires one generator size m to the gamma requires m to the gamma ancilla qubits, just because if we have a qubit over here and qubit over here, we have to actually use ancillas, making a path connecting them. So if the path is long, then we need a lot of ancillas. So we can essentially count every path required for all the generators. And since we're assuming we have just a bilayer architecture, we only have a constant number of ancillas, and we have essentially m squared paths available, where m is the size of the grid. So if we calculate this essentially gives us a circuit depth lower bound on the number of steps it's going to take us to measure some set of generators in this scheme. So yeah, here's the explanation of our lower bounds to the circuit depth, where we just have some size distribution, where we might have a lot of small generators and a few big ones. But each generator is going to take about this many ancillas, some constant. Since we're working with LDPC codes, it's going to be a constant times this. And then we have essentially m squared ancillas available each round to work with. So now that we have our scheme, we can come up with a simple greedy algorithm to do it for us. And this is essentially, this is the easiest thing you can do, where we just greedily try to fill up our routing layer with bell pairs. And essentially what we do is we go through a list of generators, we start generating bell pairs, we start doing our long range CNOT gates through gate teleportation, and we just keep going through the list of generators until we're done by prioritizing generators that are almost done. This scheme, this algorithm really only works if our partial generators commute, which is the case if we say only measure the Z type or only measure the X type at a time. So in practice, this seems to perform pretty well. If we, in this plot, we drew random examples of bivariate bicycle codes, which we looked at in the paper. And for small code sizes, around 100, 200 qubits, 300 qubits, the theory bound from the previous slide matches pretty well with the depth returned by the algorithm. However, we do see if we scale up a little bit, then it starts to deviate, indicating that the algorithm is not super optimal. But again, for experimental relevant sizes, it could be a reasonable choice to do this. So as I said before, this teleportation scheme was used before to do error correction. However, they didn't find very promising results. And so we added, or we first figured that maybe the result of this is that teleporting these CNOT gates actually increases the error rate of the resulting CNOT gate. So what you can do first is by purifying the bell pairs used in these CNOT teleportations. And if you do this, then you get higher fidelity CNOT gates, which might give you good enough performance to see see a threshold or see better error correction. And the easiest way to doing this is by generating essentially a donor bell pair. If you have your red bell pair that you want to purify, you make a donor bell pair, and you just perform the circuit. If the measurement results agree on the donor bell pair, then you keep the red one. And if they don't agree, then you just toss it. And in the cases where the measurement results agree and you keep it, then this bell pair has a much higher fidelity. And if you use it in the gate teleportation scheme, then your CNOT gate has a higher fidelity. So using the previous algorithm, we can do routing, including this donor bell pair in much the same way as before, but it complicates it, obviously. And I'd like to note that better purification protocols than this exist, but they take longer and use more qubits and bell pairs. So as I mentioned before, we use these bivariate bicycle codes, which were recently introduced, and they come from this wider family of generalized bicycle codes. The construction doesn't really matter too much, but what does matter for us is that they have this repeated parity check structure, and they have a few the small percentage of generators that are large. And what I mean by large is that they cross this long boundary for specific embeddings. And this repeated parity check structure is essentially a translational symmetry of the checks. And this just allows us to manually create routing schedules that are fairly optimal. And as an example of these short and long range generators, here's a BB code, and I have highlighted a short range generator versus a long range generator. And if we do our routing scheme, our gate teleportation scheme, then we can see that doing this generator is going to take a much longer bell pair, because we actually have to stretch all the way down here compared to just doing this one, which requires smaller or shorter bell pairs. And here's an example of a routing schedule that we found by hand for another BB code for the short range generator. So any of the ones that don't cross the boundary. And I have included the the pink donor bell pairs that we need to do the purification. And we can see that we can do this in 5 steps, essentially. The circuit depth actually is about 10 times longer than this because we have to do the bell pair generation, the purification, and then the implementation of the CNOT gate. And if we were to do the long range generators, then it would also add more routing rounds. So the main drawback for this scheme is that the syndrome extraction circuits are pretty deep. So it only works in some error regimes. So to help with error correction, we also do this partial syndrome QEC. And this is formalized by this masking idea, which is the process of removing generators from the stabilizer group during some QEC rounds. And I have removing in quotes because we're not actually removing it from the stabilizer group. We're just neglecting to measure them in some rounds. So the purpose for this is we saw that there's few long-range generators, but since they're requiring more or longer CNOTs, they're going to take essentially longer to measure. So instead, what we can do is we can measure these long-range generators less frequently and still hope to achieve similar logical error rates as if we were to measure all of them. So we can potentially decrease the circuit depth, which yields fewer idle error locations and then a lower effective error rate. So for example, if we have some error correcting code and we measure the long-range generators every 10 rounds, then the circuit we get is about 35% shorter than if we were to measure every generator every time. So could be some significant savings in circuit depth. Okay, so we've done all the building blocks and we're gonna put them all together into circuit level simulations to see how this performs. So we know how long it takes to route, purify, and measure the generators for specific code embedding. So we know how long or how much idling error to apply. We also know how many long-range generators there are. Based on our purification scheme, we also know how well your purification performs. So we know what the resulting error rate of the CNOT gate is. And then we also know how often the purification fails. So we know when the short range generator or all the generators should be available. I should note that in our scheme, if a purification fails, then we kind of just neglect, we just give up on the generator instead of retrying it. So this adds into this partial error correction scheme, and it turns out that the performance doesn't suffer too much. To decode, we do this circuit level decoding, which has been used in a large number of recent QC papers, has shown to be pretty well performing. But just in general, we build this circuit level bipartite graph, which we can use to correct errors. And this bipartite graph essentially has check nodes, which are called detectors, this parity of time adjacent syndromes. And then we have bit nodes, which are the errors in the circuit. And then we connect these check nodes and bit nodes if an error is detected by this detector. The novelty for this work is that with the partial syndrome QEC, we might have to look a few rounds back to get the syndrome difference. But practically, it doesn't really change much how it performs or how it functions. So for the circuit level simulations, we compare it against the surface code, and we extract the logical error rate per round to quantify how well it performs. I'd like to note on this slide, this panel right here, panel C, we changed the rounds at which the long-range generators are measured. Instead of every 1 round, we do every 5 rounds, and we find, at least for this code and this error regime, they perform pretty well. So presumably masking has minimal effect on the logical error rate. Now, if we plot the logical error rate versus the total space overhead that we use in the scheme, we can see that these BB codes implemented are outperformed by surface codes at small enough sizes. However, if we scale up, eventually we start to see better performance out of them than the surface codes. And if we scale up the number of logical qubits to 12, then
they immediately start performing better. And like I said before, the main drawback for the scheme is the long circuit depth. So if we have error rate that is lower, or in this case, no error rate, then we see way better performance out of the BB codes than the surface codes. So in conclusion, we've introduced a physically realizable 2D local architecture for implementing non-local quantum LDPC codes. We've developed bounds and a greedy algorithm for performing syndrome extraction circuit using LOCC routing, gate teleportation, and Tailwind purification. And then with numerical simulations, circuit level simulations, we showed that bivariate bicycle codes implemented in the scheme have comparable performance to surface codes, but they use fewer qubits. I should note that the scheme is general in the sense that if you have a different code, if you have a hypergraph product code or whatever, you can apply it in the scheme as long as it has an embedding that you want to use that is has a nice embedding. However, as I said, this is probably only viable in certain error regimes, or if you can isolate the qubits, the data qubits, while we're doing this Bell pair generation and stuff in the routing layer. So it remains to be seen if this is like where we can use this or in what devices. And with that, I'll end and take questions.
Thank you for the great talk. I'm wondering, how did you decide the criteria of the long range in your change of the syndromes? And I'm also wondering, how do you change your decoding when you remove some of the syndromes?
Yeah. So these BB codes, they have nice embeddings actually. They have like a twerk, they call it a twerk layout, where they have 4 short range and 2 long range qubits in each check. And you can go through each code and it has a number of different embeddings. And if you choose codes where the grid that it's embedded on is like skinny and tall, then you get a few number of these long range checks and then a lot of these short range checks. So mainly we looked at codes where this is the case, and then it's only the checks that like cross this boundary, like cross the long range boundary. We consider those the long range checks. So it's always like deterministic based on the embedding. Yeah, the decoding is really simple. It's not really changed at all. So like when you, there's supposed to be a syndrome here, right? But there isn't. So then when you get this syndrome, if you're gonna find the detector, which is the notation for this, which is just the parity of the current syndrome and the previous one, you just look from this syndrome back to this one. And then this detector forms like a node in the graph. And essentially all this comes down to is that there's gonna be more errors in here that are associated with this guy. Whereas, up here, it's gonna be split over these 2 detectors essentially.
Any more questions?
Hey, yeah, thanks for the talk. This is really cool. If you, I guess, yeah, you had these long range stabilizers that were kind of not over the boundary, and then you had the ones that were really long because they're over the boundary. If you got rid of the really long ones by like maybe having some other way of connecting the top to the bottom boundary, do you think that would make like a huge difference or only a little difference? Does that make sense?
Yeah, so I think I think you lose a lot for these codes, at least, if you didn't consider them on a toric layout. If you just considered like a planar one in which you'd lose these.
I guess,
essentially.
sorry, I guess I was thinking like, let's say you could create a entangled pair of photons and then interact them at the boundary and like do the super long ones in a completely different way and only do this teleportation thing for the medium sized ones.
Yeah, that would actually work great because for like the comparison between the time it takes to do a bunch of these short range ones versus a few of these long range ones, they're like almost comparable. So it takes like just as long to measure these 15 checks as it does to measure these like 40 checks. So if you could cut down on this, you know, the overwhelming fraction of the time that it takes to measure these very few checks, then yeah, I think you'd expect to see some benefits.
Okay, thanks.
Got one simple question. Maybe I missed it, but do you get a threshold with your scheme?
So yeah, we don't do an asymptotic sort of calculation, but we experimentally see that increasing the block length decreases error rate. And this is, you know, in comparison to the Delphos, Beverland, Tremblay paper where they don't see any increase. They actually see the logical error rate go up if you increase the block length.
Well, do you believe that you could like theoretically derive a threshold by this like purification idea?
Yeah, I think there's, if you consider the asymptotic scaling of the purification scheme and then the maybe a more rigorously defined routing schedule, then perhaps you could.
Any other questions? Right, let's thank the speaker again.
Hello? Oh,
Yeah,
this works. This is the pointer. Hello? Okay.
So the last talk of the session is going to be by Xiang He, and he's going to tell us about single shot decoding of good quantum LDPC codes.
Hi, everyone. Thank you all for being here for the last session of today. My name is Sunny. I'm a grad student from MIT. Today, I want to tell you a little bit about this problem, or just this general regime of decoding quantum codes in single shot, or in general, trying to reduce the quantum time overhead one needs to pay for decoding a quantum code. Now, the subtitle of today is Protecting Memory with Constant Time Decoding. I'll explain what I mean by constant time decoding towards the end of the talk. Okay. But let's start with the title. There's really a lot of words here. Each of these words carry quite some meaning. So the structure of today's talk would mostly be that we'll go over some of these keywords, and at the end of the talk, we'll be able to put together a complete picture of what this work is really about. Okay. Let's start with quantum codes. This is the last session of the quantum error correction, so allow me to not go into too much detail. But the high-level idea is very clear. We take k qubits of logical information, encoded into n qubits of physical information, and this physical information goes through some kind of noise, a particular noise channel. And given this noisy state right here, our goal is to do some projective measurements. We've been talking about stabilizer measurements, and correct back to the ideal physical state. Okay, so for today's talk, we'll focus on the decoding part of this whole story. And let me illustrate a lot of these examples, both in terms of decoding and in terms of single shot decoding, with our favorite code, with everybody's favorite code, the Tora code. Okay. I think I don't need to spend too much time introducing it, but the Tora code is defined on a lattice where you would put qubits on the edges of the lattice, and you would put X checks on the vertices of the lattice. Each X check is acting on the 4 adjacent edges. Similarly, you put Z checks on the squares of the lattice. And the decoding problem is that when a particular error, let's say Z error, happen on some edges, you flip the syndromes at the endpoints of the edges. If you have a line segment like this, it flips the endpoints on the line segments, right? So this is the very standard Tora code error and detection model. Now, the decoding problem says that if you observe, because when you're actually in your physical hardware, you don't really see the error, so you see all of these syndromes. So the decoding question is, given these syndromes, how do I find the most likely error correction to fix the syndrome? And in the case of the Tora code, this is very simple. You find the shortest line segment that connects your syndromes together. This is called minimum weight perfect matching. So now on the Tora code, this has been studied many, many, many times. But in a more realistic setting, your measurement gadgets are also noisy and are also imperfect. So the question is, what happens if our syndromes could be wrong too? So let me explain what I mean by that. Let's consider what's called the phenomenological noise model. And in this particular noise model, you have Pauli errors on your qubits, and you have potential flip errors on your syndromes. What does that mean? So suppose this is the true error, the error that happened with 2 true syndromes that should have been flipped. But when you're actually doing your flip in your lab, extracting the syndromes in your lab, what happened is that one of these syndromes disappeared. Let's say the blue one disappeared, and a fake syndrome, a green one, appeared. Then to your observation, this is a completely valid syndrome. I have 2 syndromes on my lattice, and I should correct it with such a correction, which is completely wrong. So what is this example trying to demonstrate? Is that in the more realistic setting, well, in the most realistic setting, we should talk about circuit level noise, but in the more realistic setting where the syndromes could be wrong, is that the Tora code really cannot protect against this kind of error. If you flip a few wrong syndromes, you get a completely wrong correction. And the question is, what can we do? How can we decode when your syndromes could be wrong? And there's a very natural and a very standard solution that has been applied in a lot of different settings. And that is, why don't I just repeat the measurement for D rounds? And this is very natural, this is very intuitive. If I'm not sure about my measurement result this one round, let me just do this again and again and up to D rounds to be more certain about what my measurement results here should truly be. Okay. So this is, again, this is a very standard approach. And in this case of Torah code, when you repeat this for D rounds, the decoding procedure you would apply is called space-time decoding. It's really a matching instead of 2D in 3D, where 2 dimension is space and 1 dimension is time. This is discussed in the very early paper on surface codes. But the question that we want to discuss today is there an alternative? Right here, I need to measure syndromes for D rounds, which is a really pretty heavy time overhead for decoding. And the question is it possible for me to do this decoding with only 1 round of noisy, mistaken syndrome information? And this is the idea of single-shot decoding, which is, suppose you give me not D rounds, but just 1 round of syndrome information. Can I still reasonably do this decoding task? And what does reasonable mean? Reasonable means that we'll decode it such that the residual error is small. There's no way I could do perfect decoding when my syndrome is wrong, but can I at least guarantee that the residual syndrome is small or reduce the problem? And we see that if this is possible, this would really reduce the quantum time overhead of this decoding by a factor of D. And this is actually very motivated from a realistic and practical standpoint, because the more rounds of circuits, syndrome extraction circuits you need to do, the more errors and noise accumulate, and you definitely want to save these time overheads. So this is formulated as the topic of single-shot decoding. And as we have seen earlier with the example of Torah code, as is the case for a lot of different codes, this doesn't work. You can't just give me 1 round of noisy syndrome information and expect me to be able to work magic. But what's the fundamental, or what are some really important issues or barriers to, for instance, the Torah code or a lot of other codes that we see from being single shot or from being resistant to measurement errors? Okay, but so let's again use this example. There are really 2 issues here that's stopping this Torah code from being single shot, or just in general requiring less measurements. And the two issues is there exist these very large errors. So think of this orange line as 1 error. There exists these very large error with very small syndrome. And on top of that, I could flip these syndromes like we saw in the previous example where 1 syndrome disappeared and 1 appeared. There are very easy ways for me to flip these syndromes without being detected by the code. Because when the code sees 2 syndromes on the surface code or on the Torah code, it just say, oh, this is a valid syndrome, I'll do decoding as usual. It is undetected. So this is really the 2 main issues that require this kind of D rounds of repeated syndrome extraction. And single-shot decoding, as it's proposed, has been studied in quite a few settings. And up to now, we have really understood 2 ways to, I guess, counter these issues or to build codes to resolve these issues and make them single shot, or in some sense, more single shot. And the 2 methods that we have, one of them is to use local redundancy in your stabilizer checks, and the other one is to use expansion in your underlying Tanner graph. I explain both of these on an intuitive level in just a bit. So to explain those 2 intuitions, let's go over some examples of single shot codes that we currently know. One such families are the topological codes that are some of the topological codes. That includes the 4D Torah code, 3D subsystem Torah code, etc. And the important thing here is that these codes have what we call local redundant checks. Okay, what does that mean? That means that locally, you can't just do what's happening in the Torah code where 1 syndrome disappeared and another one appeared and you just cannot detect it. There are these redundancy in your checks, which means a check could be the product of a couple other checks surrounding it, so that if that check got flipped, the other surrounding checks is there to tell you that there's an inconsistency in my checks and tells you that there's a measurement error. So that's a little vague, but the key idea here is that using these local redundant checks, we can really detect and correct measurement errors that happen, not just the physical errors happen. This is more of a method to directly attack the measurement errors. So these codes are known to be single shot. There's another different regime of single shot decoding, which is based on expansion, which says, suppose you take a quantum LDPC code. I think we know what LDPC mean now. But suppose we take a quantum LDPC code and I look at the adjacency graph between the checks and the qubits, and this adjacency graph is expanding. Then this really avoids the problem of having a large error that I would like to correct that have a very small syndrome. Okay? And so one known example, which is single shot, is this quantum expander codes work from 2018. And in this paper, we extend this regime to the quantum Tanner codes, which is a family of asymptotically good codes. I'll go into these details in just a bit. But the ideas in these two work would be quite similar in the sense that we'll make use of the expansion of the underlying code structure to achieve single shot instead of using local redundancy. Okay? And there's a way I could make the instead of part of the sentence very precise, but let me not do it here. But we see that each of these, either using local redundant checks or using expansion, is trying to attack one aspect of what I mentioned earlier as the two issues, having a large error with small syndrome or having these syndrome errors that are undetectable. Okay? So this is kind of the landscape of single shot decoding. And if there's a nugget I would like you to take away from my talk, this will be one of the nuggets. And I would also like to point you to the work by Campbell, which really formulated this whole idea of using redundant checks and also constructed a bunch of codes with redundant checks in the language of using meta checks and using chain complexes, which I think is extremely helpful for understanding single shot. So this is the overview for single shot. Let's go into a little bit more about good quantum LDPC codes. So as used in maybe all previous talks in this session, quantum LDPC codes, the definition is simple. All the stabilizer checks have constant weight. All the qubits are touched by a constant number of checks when you scale the family larger. And what are asymptotically good codes? Well, the definition is also simple. The number of logical qubits, your logical dimension, and your distance scales linearly with your number of physical qubits. And up to now, since 2021, we now know 3 families of asymptotically good quantum LDPC codes, which are all based on the same underlying idea, the same underlying mathematical idea and intuition, which in this talk, I will phrase it as the left-right Cayley complex, which a lot of you may have heard being mentioned across board. But for our paper, we focus on this family introduced by LeVere and Zamor called quantum Tanner codes. It's one of the families that's perhaps easiest to study among the 3 families. And yes, we'll talk about how the quantum Tanner code is constructed. I promise to not go into all the technical details, talk about how decoding works, and we'll talk about where we get the single shot from. Okay, great. So let me start with the left-right Cayley complex. And I'm sure we have heard a lot about left-right Cayley complex, and the construction is not very simple to understand. Here, I want to really sketch the important intuition of what is the left-right Cayley complex while hiding a lot of the technical details. So how do you build it at home? Well, you take a group G, and you take 2 generating sets A and B. And what you do is you take 4 copies of the group G. And in this case, I'll draw them a little disproportionate because this figure here, I'll tell you later, is really only the local neighborhood of 1 vertex. Okay? But so right now, let me draw them a little bit disproportionate. Assume you have these 4 copies of the group G. They should be the same size, even though they're not drawn to the same size. Now I'm going to create 2 types of edges. So when I have these 4 copies, what I'm going to do is every group element is going to be a vertex in my graph. I'm trying to build a big graph here, big expanding graph. And I'm going to create 2 types of edges in this big expanding graph. The first type of edges are going to be the A edges, and one should think of them as going vertical. And how are they constructed? You take a vertex G here, and you take an element A in the generating set capital A, and then you connect it to AG in this set. Okay, so you are going to create all of these edges between every pair of G, AG, between these 2 sets of G and these 2 sets of capital G. So you get all of these A edges going upwards. This is just like how you would construct a Cayley graph. Therefore, the name left-right Cayley complex. Now, you will similarly create the B edges. You will connect the vertices here to vertices on your right, these horizontal edges, based on elements in B. And that's it. That's really the construction of the left-right Cayley complex. I've hidden a lot of details. How you pick this group G, how you pick these two generating sets, those are actually very important to building the left-right Cayley complex. But the geometric structure that I would like you to keep in mind is really this geometric structure, right? So this I call the local neighborhood of this one vertex little g. And let's take a look at this local neighborhood. I created a bunch of A edges going up. I created a bunch of B edges going to the right. And this, when I look at these two type of edges together, I really see a lot of squares. Where did those squares come from? The squares come from the fact that if we look at this red square right here, you're going to connect the vertex G to A3G and to GB1. And A3G and GB1 will meet at the same vertex A3GB1 that's belonging to G11, capital G11, this copy of the group. You get a lot of squares like this when you construct this left-right Cayley complex just by specifying the edges going up and this going vertically and the edges going horizontally. And these squares are extremely important for our construction of the quantum Tanner codes. Because what we do is that you take the left-right Cayley complex you just built and you put a qubit on every single square that you see. So how many squares are there? Well, I'm looking at one local neighborhood right here. I have a total of A edges going up or going vertically. I have a total of B edges going horizontally. And each pair of A edges and B edges is going to give me a square. So this one vertex, little g here, is going to see A times B many squares. And therefore A times B many qubits. That's in its local neighborhood. Okay. And how I'm going to build the code. So I told you what the qubits are. I should told you where the checks are. And the checks in the quantum Tanner code is, well, I won't go into the details of how they're selected, but essentially for each vertex G, you look at its local neighborhood, which has a bunch of qubits. And what you would do is you would design a set of X check, which acts only on the qubits in its local neighborhood. This is very important. I have not told you how you construct these checks, but I have told you that these checks are restricted to the local neighborhood, that it doesn't touch the local neighborhoods of other vertices G. Similarly, you will build Z checks on these two sets of the group G. You will look at the vertices in here, you look at their local neighborhoods and build Z checks as restraining to those qubits. Hiding a lot of details here, but you just built your own asymptotically good code. It's really nice. It's has a lot of amazing properties, and it's actually the easiest to work with among the asymptotically good codes that we know. Okay, great. So this is the code construction. I really sketched it, but I hope that you could at least take away some of these intuitions. Let's now go on to talk a little bit about how we are going to decode such a expanding construction. So what would the decoding problem be? You are going to see a bunch of syndromes. Some errors are going to happen. You don't know where the errors are, and you're going to see a bunch of syndromes. Where are the syndromes? The syndromes are on the vertices in G00 and G11. These are the X checks, or the X checks lives on the local neighborhood of these vertices. And the decoding problem is that you now need to find qubits, which are these squares to flip to correct these syndromes. So as we discussed earlier, every vertex G sitting here really has its own set of stabilizers that's acting on its own set of local qubits in its neighborhood. So if my goal is just to fix all the stabilizers on this one vertex, that's actually really simple because it's a very local problem. It's just a set of checks acting on a constant number of qubits. And I could just find a flip within those constant number of qubits to correct all the syndromes here. And similarly, I have many vertices here, but I could correct each of them individually because the checks are restricted to local neighborhoods. What did I just say, or what do I really mean? What I mean is I could easily find a correction C00 that will fix all the syndrome in G00. Now that does not solve our problem. That doesn't even solve half of our problem because the other half of syndromes, G11, is not going to recognize that correction. It's going to say this correction flips a bunch of syndrome on me. It doesn't do anything good for me. Okay? But this does solve all the syndromes on G00. And similarly, you can find a correction C11 that will fix everything for G11 and flips things here that is erroneous. And the idea of the decoding algorithm is actually very intuitive. It says, I found that each of these, really they're half solutions. They only fix half of my syndromes. Can I try to negotiate their differences? Can I try to say, oh, let me capture their disagreement as C00 plus C11 mod 2. Let me capture their disagreement. And can I really reconcile their disagreement, maybe one step at a time, so that they agree with each other? Because if they agree with each other, and we know that they correct C00 correct this syndrome, C11 correct this syndrome, and I can make them agree, then I have just found one correction that will fix all of my syndromes. So this idea is really captured with this notion of the mismatch vector, which captures how much these two half corrections disagree with each other. And the goal of the decoding algorithm is I'm going to try to reduce this mismatch vector all the way down to 0. Okay. Yes, like I said, if Z became 0 through some procedure, then I have really found two corrections that agree with each other, and therefore they will flip both sides of the syndrome. And this decoder is the mismatch decoder proposed by Levere and Zamor in a work later than their quantum Tanner codes paper. Great. So how do I really do this? It turns out that I could do this via a greedy algorithm. I'm just going to keep trying to greedily reduce the weight of the mismatch vector. How do I do that? Well, if I have a mismatch vector, let's say a large weight mismatch vector, what I would do is that using the expansion, I'm going to just give the intuition. The technicals are actually very, very technical, but I'm going to make use of the expansion of the complex to argue that when I have a mismatch vector, there's always one vertex G, little g, whose local neighborhood contains a lot of qubits that are in the mismatch vector. What does that mean? This vertex G really sees a lot of qubits that the two corrections disagree on. And I should try to work within this local region. This is the very kind of famous global to local kind of argument. What I should really do is to look within this local region and try to reduce the mismatch in that local region. And that's exactly what I would do. I'll use the robustness of the local code. I have not mentioned the local codes at all, but think of this as just some really nice property of the local checks I'll put onto this local neighborhood. I'll use this really nice property to say I can always find a good flip that will reduce the weight in this local region of the mismatch vector. So with these two really, really important and nice property of the quantum Tanner codes and also of all of the asymptotically good codes that we know so far, we're able to do this decoding algorithm greedily so that at the end, you are left with a valid correction and you can correct linear weight errors. So, okay, this talk is not just about decoding. This talk is really about single shot decoding. So what if there are measurement errors? Why exactly can I do this decoding procedure when there are measurement errors? And how exactly can I achieve this single shotness because let's keep in mind, this code has linear distance. If I adopt the natural approach where I repeat measurements for d times, that's actually a lot of times. Okay? But why is it that I could use one round of noisy measurement information to do this decoding to a reasonable level? Well, the idea here, the intuition which I'll explain is quite simple. So remember that what we're really using is a greedy local decoder, which means that if I have all of these measurement errors that happen on my syndromes, well, I can really say, well, each vertex here has a set of its own check. Some of those checks are flipped by a measurement error. I can really decompose this global measurement error into a bunch of local errors onto the mismatch vector. Now, given these local errors on the mismatch vector, The expansion property that we referred to earlier will say that when you have these local errors, it does not hurt the global expansion of your complex. And you can still find a vertex G that hits a lot of mismatch. Even though these mismatch are no longer correct, they are erroneous mismatch. But most of the mismatch that you found are still going to be correct because the errors are in the end going to be low weight. Okay. And you use the robustness of the local codes again, this is a very nice property to say that even though the local mismatch that I see at each vertex is erroneous, I can still find a flip that will reduce the weight of the mismatch, even though it wouldn't be correcting as it does in the noiseless setting when your syndrome is completely correct. So this is, I'm really going to sketch this argument just like this, in the sense that when you're hit with measurement error in this kind of, in this quantum Tanner codes, when you edit the decoder so that you take account of this measurement error and you decompose that measurement error into local errors on the mismatch vector, utilizing a similar argument of this expansion and robustness of local codes, utilizing this argument of global properties to local properties, local properties to global properties, you're able to do a correction such that the residual error will be small. So let me give some more formal statement of what we have actually proved. Okay? There are three main results that I would like to mention here. The first main result is as stated, it's the single shot decoding of quantum Tanner codes. And there are a few points I would like to mention. So first of all, the decoder that I just mentioned, the greedy decoder, it's a linear time sequential decoder. Why do I say sequential? Because we are going to see a parallelized version in just a bit. So you take this sequential decoder in Laverne-Seymour, we need to make some edits to it to do this decomposition of the mismatch vector, but it's single shot in the following sense. So you have a qubit error E, you have some syndrome error D, and suppose E and D are just arbitrary errors. This is an asymptotically good code. We could be in the adversary setting. Okay, they're just arbitrary errors that have weight that's linearly bounded. It's an asymptotically good code that has linear distance. Then there exists a constant beta such that after you do this sequential correction, the residual error weight is really bounded by a factor of the weight of the measurement error. Why does this make sense? Because like we said at the beginning of the talk, when you have measurement error, there's no hope of correcting it to perfect because you don't have the correct syndrome information. You would hope that you can correct down to a reasonable level where your residual error is small. How small should your residual error be? Well, you would hope that the smaller your measurement error is, the smaller your residual error is. And you would hope that this error E, the weight of this actual error E, does not show up in the equation. And that's exactly what we show here, is that when you apply this linear time decoder, the sequential decoder, the residual error weight will be bounded by a factor of the measurement weight, error weight. And so since we talk about adversary settings, stochastic errors are also covered. This immediately gives you a threshold, blah, blah, blah. Great. So the second main result that I would like to mention is that there is a fairly natural way of parallelizing the sequential decoder earlier, precisely because all of these decoding and correction procedures are done within the local neighborhoods that I keep stressing with that figure. But if you do this parallel decoder, then the parallel decoder is single shot in the following sense. So suppose you have E and D, which is your measurement error and syndrome error as before, linearly bounded in weight. And now with this parallel decoder, the parallel decoder will, suppose you run the parallel decoder for O of T steps. I have not defined what steps mean, but think of it as just O of T runtime that you allocate to your parallel decoder to run. And the residual error weight is really, you have this factor of D as before, but you also have this exponentially decaying factor of this original error weight E. How should you think about this? Well, if you want to correct, like before, correct to as much as you possibly can to get rid of all the actual error, you just need to run T for T equals to log n, which means you run your parallel decoder for log n iterations. And which means we really have a log n time decoder that's perfectly single shot, just like this one. But this also gives you the freedom to choose how many iterations do you want to run your parallel decoder. And this is where we're going to get into the regime of constant time decoding. So let's look here. If t is a large constant, then my residual error weight is really exponentially restricted in the weight of the actual error with some constant factor on the weight of the measurement error. And what we showed in the third main result is that suppose you have a decoder with the single shot property that we have discussed here. Then if you consider building a quantum memory based on the quantum Tanner codes or these asymptotically good codes, and it's experiencing bounded noise, then by running the parallel decoder for a constant number of iterations at each QEC step, so constant round parallel decoder for each QEC step, you can really keep your quantum memory alive, which means no logical error happening, for an exponential, and when I say exponential, I mean exponential in n, exponential number of rounds. So this is a fairly surprising result that when we first worked it out for the following reason. Because when we talk about single shot decoding, the motivation has always been we're trying to reduce the quantum runtime. Instead of having to measure the same circuit d times, I really want to only measure it once. But here, we are also reducing the classical runtime of a decoder from usually linear time to parallel log n time, and in this case, to constant time decoding. So the time overhead, the classical and quantum time overhead of decoding with the quantum Tanner codes is both constant. And so this really, we really think that this result is a good indication of how we should think about single shot decoding practice of trying to maintain a quantum memory. And asymptotically, if we want to build a fault tolerant scheme based on these quantum Tanner codes and by extension, these asymptotically good codes, how we should think about the time overhead of protecting the memory. Okay. That's the end of my talk. Thank you all for being here.
Questions?
Thank you for the amazing talk. I'm wondering for the single shot decoding scheme here, would they be able to be extended to the other two families of good QLDPC codes?
That's an amazing question. So so the three constructions are really based on a set of very important, set of very insightful mathematical observations that are the same observation with this expansion of this global complex and this robustness of the local codes. And therefore, the three constructions are really they're different, but they're quite similar in spirit. And the proof, so this decoder will not work, obviously, on the two other codes because they're constructed differently. But since they're based on the same ideas, and we think that the single shot property holds for the two other families.
Okay, thank you.
So I actually have a question. Thank you for the very accessible description of the Tanner code construction. I'm just wondering if you could comment on the group that is necessary in it. Can it be any group? Are there restrictions on it?
Oh, no. Well, you can build the graph with any group that you want. But to get to asymptotically good codes and to get to these left-right Cayley complexes, which have very nice properties, you need them to be very specific groups. I think the citation here is these LPS matrix groups, such that when you pick this huge group, so you need to pick a group and two generating sets. We need these generating sets to be constant weight relative to the size of the group, so you have a growing family of groups. The generating families A and B needs to be constant weight, and they need to be very carefully selected so that the resulting left-right Cayley complex is going to have the expansion that we need. So yeah, picking that group is a whole nother line of work that, yeah.
I see. Thank you very much.
Okay. So you had this comment on the single shot decoding and like codes which are single shot decodable kind of falling into two groups, either having like meta checks or having expansion. I always feel like some kind of compulsion to comment on this because it's very prevalent in the literature to say this, but it's, I think, quite misleading and not really true. So you can, for example, run flip on like you gave the example of the 4D toric code.
Mhm.
So the actual, like if you read the original like Dennis et al. Thing where they talk about this as a self-correcting memory, the decoder they use is basically just parallelized flip.
Mhm.
So it's not really using the meta checks at all. It's just using the fact that the code has this confinement property
Mhm.
where the syndrome weight is somehow like non-constant in the error weight. Yeah, so just like to this point, you don't necessarily need to have expansion because it's just a cubic lattice, like it's not expanding.
Mhm.
And you don't need to have, or you don't need to utilize meta checks in the decoding.
Mhm.
All that you really need is this confinement property.
So my understanding with the cases with topological codes is that you may not need to explicitly use the meta checks, but for most of these single shot decoding paper that I understand, you need to have redundancy in your checks, which is, I think, I think we had this discussion at the previous workshop where we were talking about confinement versus soundness versus all that. But I think the redundancy in your checks is a very important component to make sure that the decoder works single shot, right?
So I think that the you could kind of say that the fact the redundancy exists, at least like you have like some non-constant number of redundancies in the code size.
Yes.
You probably cannot have this without inducing confinement in your code.
Mhm.
But I suspect that you could also look in like a lot of these like asymptotically good codes
Mhm.
and find lots of things which look like meta checks, right? You'll have invalid
Oh, yes,
syndromes.
absolutely.
Right.
They have a lot of redundancy. as well.
Exactly. But you are not using any of these in your decoder either, right? So
No,
then it's like, is it really the existence of the redundancies that is making the decoder work? Like,
I see your point. I see your point. Yeah, so as in the case of these asymptotically good codes, the codes do have a lot of global redundancy. We did not need to explicitly make use of that in the decoding process to show that it's single shot. So yes, on that point, I do agree. It's an observation that these single shot properties seems to all exhibit these kind of large redundancy, which I think makes a lot of intuitive sense. A lot of decoders do not explicitly make use of them.
okay, thanks.
Right. So if there's no more question, then let's thank Sunny again for the nice talk.
I've been told I have to kick you out of this room, so please leave. Thank you.